Thank you. So I have about a half hour. I'm going to spend about 20 minutes going through some content, and then hopefully we'll have some time for questions, and we'll go from there. So I'm going to talk about ARM and disaggregated rack. I run capacity engineering and analysis at Facebook. Essentially what that means is my group has capacity plans for all the major services that we build, and we also spend all the money. So we do a lot of thinking about how unit costs change over time, and how we can drive a lot of costs out of our infrastructure. So I'll spend a little bit of time talking about Facebook scale and just kind of give you a perspective on where we're coming from. And then we'll talk about mobile processors, which is kind of my code word for ARM processors in general, and Atom and MIPS, essentially just the smaller processors compared to the x86s. And then I'll talk a little bit about disaggregated rack, which is something that we're also pretty passionate about. So Facebook is in 4 domestic regions today. We've got Europe coming online later this year, and 82% of our users are outside the United States. We have 1 billion users, 350 million photos are added each day. I saw an analysis about a year ago that indicated that we received about 1/4 of every photo that was taken, just period. So if it's a photo and it's taken, then we get about 1/4 of them. Lots and lots of likes, things like that. So all of these are just indicative of just massive scale. And at this scale, we really do think a lot about efficiency. So in the first 9 months of last year, we spent about $1 billion on servers, networking equipment, storage, and data centers. So to give you an idea of our architecture, this is basically how Facebook works. We have 3 types of clusters. Now when I say clusters, they're both groupings of servers, but they're also in all of these servers are within the same network cluster. So we used to do a 2-post cluster, now we're doing a 4-post cluster, but essentially networking clusters have gotten large enough so that we can do about 300 cabs, about 300 racks of servers per cluster. And this, what we're describing at the top, is 250 racks of servers. It's about 10,000 servers, web servers. We've got about 144 terabytes of cache, and this is in each one of our front-end clusters. We have many of these front-end clusters, but each one operates independently from the others. They all have a local cache, and it's important that they operate independently because you can have a problem, maybe you've got cache corruption, any number of things, and you want to be able to roll that cluster and take it out of service and put it back in. But the front-end clusters are dependent on the service clusters, which have service-specific sorts of things. So probably 5 years ago, we only had web servers, cache servers, and database servers. And so anything you did happened in PHP on the web server. That's terribly inefficient in terms of indexing data, and so we started coming up with all of these very dedicated services to index your data. So if you think of the Facebook feed, the Facebook homepage, in the center is newsfeed. And that index of data, that all of the recent activity of all of your friends, is served up by dedicated hardware, and they're racks of multi-feed servers. And so I'll talk a little bit about how those work, but essentially every little attribute on the site probably has a dedicated set of servers that have been optimized for that purpose. When we first started building hardware, it was all about stripping down to the bare bones for the hardware, right? So if you buy hardware from Dell or HP, you get lots of extra things on there which are generally never used in a data center at scale. A VGA port, I really don't need. Lots of console, lots of management stuff you can really strip away. And so when we began Open Compute, the focus was really just stripping that all away and producing a server that was highly serviceable and also very cheap. And so that was our first rendition. As we get into disaggregated rack and ARM, we're going to talk about other ways that we're approaching building larger and cheaper systems. So this multi-feed rack that I mentioned, at Facebook, for almost all of our services, a rack is the unit of capacity. And what that means is that we don't deploy 5 servers to someone, we deploy 40 servers to someone, or we deploy 20 servers to someone. And where that someone would be search, ads, feed, photos, whatever, chat, things like that. And all of the software is developed so that we know each server is aware of which other servers are in its own rack. So it has the concept of rack locality. And quite frequently, the data set that we need to address is far larger than what you can put on a single server. And so you do a lot of hash out. And so with a multi-feed rack, every multi-feed rack at Facebook has an identical copy of the last 2 days of a billion users' activity, right? So it's just, we needed n of them, so we have n copies of them. And that's because there's so many people hitting the service, right? And the way that it works is the web server will ask an aggregator, give me Jason's friend's most recent activity. That aggregator will then blast out a parallel call to 40 other servers within the rack and say, give me what you know, right? Give me your piece of the data. That data will all flow back. These NICs are really burning pretty hot. It'll all come back to the aggregator daemon, which will then sort it, rank it, figure out which friends I really want to hear from, which friends I've kind of ignored, and then send out a subset of the data to the web tier. The web tier will then render it and kind of move on with its life. But the critical piece here is that this service both is aware of the rack and also is it's very light on the network coming in and out of the rack, but pretty heavy on the network inside the rack. And that's something that we think is a really nice attribute to how we've built services and something we'd like to see more people do. So if you look at the life of a hit at Facebook, here time is going from the top to the bottom. You'll have a request come in. This might be a request to home.php, so just the main page. First thing that will happen is you'll hit Memcache and you'll do some authentication, make sure the person is who they say they are. Then perhaps it'll go and hit feed rack, so that was that multi-feed rack. It'll get the most recent stories. Once it has a list of story IDs, it'll bang the hell out of Memcache and pull in a ton of data, tons and tons of data. In fact, for every byte that goes out to the world, we have about 10 bytes bouncing around our network, so it's kind of a big multiplier on the internal network. If you miss on Memcache, then we might hit a database. Memcache is a look-aside cache. We'll grab the data, stuff it back in Memcache, do a few more lookups, maybe grab some ads to show, and then finally ship the page. This is a simplified version. In fact, we actually ship content kind of over time, but this is the basic idea. So if you're an engineer at Facebook, you can have anything you want as long as it's one of these 5 servers. If you ask for anything else, the answer is no. We do not do any customizations. There's one option, which is this server over here. You can get it with a PCIe flash card as an option. Otherwise, every one of these servers is shipped as is with no modifications. The reason we do that is for cost, serviceability, like try debugging kernel or driver issues across 150 different kinds of servers. When you've got thousands of servers, it gets to be pretty ridiculous. And so we keep it to these 5 SKUs. And each of these 5 SKUs, when we design them, we only talk to one customer. So internally, we might have 40 major services that need servers, probably 200 smaller services that need servers. But when we design a SKU and when we optimize a SKU, we only talk to the top 5. And the top 5 in terms of consuming servers are web, database. We have tons and tons of MySQL databases. Hadoop is a massive consumer of servers. Haystack is our photos server. So this SKU is all optimized for dollars per gig. This SKU is optimized for the most web CPU. Of course, this is really just putting Flash online so we can access it. Hadoop consumes a lot of CPU and disk space. And then feed is kind of a nice blend where this is the rack that most engineers like. You get a lot of CPU and a lot of RAM, right? So no variance, nothing beyond that. And what this gets us is we get volume pricing. we are able to repurpose servers. So if we provide a lot of servers to one service and it turns out they don't use them, either their product is not as popular as they thought it would be, or they have a nice efficiency win where they need fewer servers, we'll take those away and give them to someone else. If everybody had a unique butterfly of a SKU, then you couldn't really give servers to anybody else, which would be kind of a problem. Makes for easier operations. I think our DC headcount, I think our tech to server ratio is somewhere around, I don't know, 8,000 or 10,000 servers per tech. So it's really very low touch count. Another facility might have 1 to 500. Now, the drawbacks to this approach is that you don't have 5 services, you have maybe 40 services and 200 minor ones, and so not everything fits perfectly. I'll touch on this again when we get back to disaggregated rack. So as we think about mobile processors, I'm interested in mobile processors because essentially all the servers in our data center use processors that were designed for desktop computers, right? They're just bastardizations of desktop processors, right? Intel and AMD have dominated this market with their big x86 processors. So if you start thinking about the mobile world, the smaller processors for smartphones are going to pass 2 criteria in 2014. They'll all be 64-bit, which is nice, and they'll start having a high clock speed. Now, a couple of the problems with ARM processors is, in general, the instructions per cycle is really not great. It's pretty poor compared to all of the tricks that x86 has done in order to pipeline and get really good instructions per cycle. And additionally, a lot of the code that's written today is not very well optimized for the ARM instruction set. And so those two combined make it necessary for us to get up to a decent clock speed just to get any kind of reasonable linear throughput out of these processors. So for us, we're looking for kind of that 2.4 gigahertz range. But it is reasonable for us to start considering ARM, Atom, and even MIPS processors for big compute jobs. So if we think about the ARM processors and the landscape, we took probably 5 or 6 ARM vendors and then of course an AMD and Intel option. And we labeled them Wimpy Core and Brawny Cores here. And we got our best ideas about how much work they would do per processor, per core. We just normalized it. We said, look, if we needed to do this much work, how are these cores gonna line up? And so in terms of the number of cores required per unit work, the Wimpy cores, the ARM and smaller processors, needed more cores. And that's really just because of IPC and because of the instruction efficiency. And then if you look at kind of more of the x86 land, things are doing pretty well. Now, on the watt side, the ARM processors are far lower power, right? Which is good because they're also performing less. And so the problem that we're faced with is that big processors provide a cost advantage by amortizing the fixed costs of the server, right? So if you think about, if the thing that you're trying to do is a problem that needs compute, and you've got a big processor, then all of the stuff that you have to wrap around that big processor, RAM, a NIC, a rack, a chassis, all of these different things, if you then just swap in a smaller processor, then you've got a problem because all of these other expenses are now about triple the cost, effectively, right? This is one of the reasons that Intel and AMD have continually provided bigger and bigger processors to the data center world, is because by doing that, you can amortize all of this other cost out and save money, right? The same server with the same footprint now does a lot more work than it used to. So for us, we have, I think the name's horrible, but it's called Group Hug. So with Group Hug, it's a really straightforward idea. What we're saying is, or what we're looking to do, is take an ARM processor, put it on essentially a PCIe board. It's not a PCIe pinout, but that's the form factor. And rather than put one on a sled, put 10 of them on a sled. So if you've got processors that are 1/3 to 1/4 the throughput of like a dual socket x86 board, then replace it with 10 of them instead. And you'll hit about the same power density and about the same throughput density, right? So if we can get all of the costs to work out, then we can actually make ARM an attractive option in data centers sooner rather than later. And the trick here is that Facebook, we're on a 10 gig standard, and so all we're doing is just muxing up 10 1 gig NICs. Pretty straightforward. And we're replacing one big computer with 10 smaller computers. Thankfully for the web, it's very easy to find almost infinitely parallelizable problems. Web servers, it really doesn't matter if you're doing a big web server or a small web server. There's a couple of gotchas in there, but it's not too hard to deal with. Now, the thing that this doesn't address is it doesn't address all of the peripherals, sharing of flash, drives, things like that. So I'm going to very quickly go through disaggregated rack, which is the other component that we think is probably necessary in order to make ARM a strong candidate in the data center space. So with disaggregated rack, we want to solve two problems. We want to look at, can we build hardware that will fit services, because this is what we're mostly passionate about, and still do well in terms of serviceability and cost? And can we build hardware that will grow with services over time? And I'll outline those problems. And then just in general, what might it look like to support this group hug? What might it look like to support smaller processors in the data center? So if we deploy a type 6 server, which is a type 6 is just a big RAM, big compute server. And if we deploy it to multi-feed, so the box is the amount of resources that are available, and this line is how much RAM is consumed. It turns out that all engineers always consume whatever RAM's available, so that's never a problem, right? So RAM's always maxed out. But with multi-feed, it's a perfect fit, right? RAM and CPU, they consume exactly what they've been given, and they love it. And of course they love it because we designed this server for them, right? Now, if you look at another service, and this might be like search or something like that, they'll consume all of the RAM, but maybe only about half the CPU. And it's just because their particular compute needs are not as high as, say, multi-feed, right? And so it would have been better for us to give them half as much CPU in the same chassis, right? The other thing that happens is that services change over time. So a service that maybe fit very well in year one doesn't fit very well in year two. And what this means is that we're going to end up either doing something ridiculous like cracking the cases and upgrading processors, which is very hard when you've got 1,000 of them, or we're going to end up buying more servers and essentially underutilizing the other resource, maybe RAM in this case. And so if you think about resources that can be consumed by any service, and this is just at scale, you've got your basic building blocks, RAM and CPU. You've got disk IOPS and disk space. You've got flash IOPS and flash space. And then you've got common resource pairings. CPU and RAM are usually two things that you trade off. Maybe you'll do compression in memory. Maybe you'll do some caching to avoid some wasted CPU churn. RAM versus disk IOPS is a classic, and RAM versus flash IOPS is another classic trade-off. And then you've got some resources that strictly grow over time. How much RAM you need over time might increase as your service changes, and certainly disk space and flash space tend to increase. And so what we think is that we can build hardware that's highly configurable and reconfigurable and still cost effective. And so if you think about a rack of multi-feed servers, and rather than think about the individual servers, think about the resources that are within the rack. You got about 6 terabytes of RAM, 80 terabytes of storage, 30 terabytes of flash. This is in one of the variants on the services. And what would it look like to actually just provide each of these resources independent of one another? So rather than put them in pairings, allow being able to add a little bit more compute or a little bit more RAM without cracking cases and adding extra DIMMs. And so we think that we can build 4 standard kind of server types, or 4 standard sleds. One is a compute sled, which on the left is kind of a standard sort of x86 sled, which would be 2 processors, bunch of DIMMs. We'll get rid of the hard drives and just have a nice big NIC. In group hug, we're talking about 10 servers, few DIMMs. These will end up about the same amount of compute power, about the same amount of power density and throughput density. So we have the idea of like a compute sled. Then perhaps the idea of a RAM sled. Now, when people have thought about disaggregated rack or disaggregating resources in a computer, they often think about having random block access to RAM, and we're not proposing that at all. We're really just saying a nice key value store, which is rack local. So you can hit it as much as you want, but it's not block access, because as soon as you try and do remote block access, even over optical links, you start dealing with many nanoseconds delay. You try to walk RAM with lots and lots of delay, lots of latency, and it's not going to work out. So we're really just saying key value pairs. And architecturally, software engineers are going to want to think about this as kind of like FAR RAM, something that you page in and then do some work on, right? Then as we get over to storage, this is an open compute project, Knox, where this is a SAS expander, and then typically you'd have a bunch of SAS cables coming out to get cabled up to a computer. We're just going to pull this out and replace this SAS expander with a computer with a 10 gig NIC on it. So it's really just putting hard drives directly on the network. And then flash sleds. So we think flash is really useful. And this is kind of our basic poke at, if you've got this much NIC, about how many IOPS and about how much flash capacity do you think you'll need. Now you notice here that these NIC speeds are getting ridiculous, right? So 1 gig is really a lot for almost any server. 10 gig is really more than you'd ever need. When you start disaggregating resources, you really do need a ton of bandwidth. And the only reason we're proposing this completely absurd thing of disaggregating all of these resources is because the interfaces that are available today are starting to get really reasonably cheap at 10 gig, 40 gig, and even with Intel has the silicon photonics stuff, which is actually 4 25 gig links per server. And they've got a route to probably 400 gigs per server. I mean, it's like beyond insane, right? And so what it's essentially looking like is that we're getting in a realm where we have, for really pretty cheap, almost unlimited bandwidth within the rack. And so we're really looking to capitalize on that. So if you think about our, let's say our graph search, we launched it a little while ago. We might start out with about 3 terabytes of RAM, 60 TB of drives, and then 30 TB of flash. And maybe year 1, this is their mix of resources. But then later, in year 2, they find out that they've done some efficiency work, and they can actually, for the same amount of RAM, they can support more flash. And so maybe they want 40 terabytes of flash. And so in year 2, we add more flash to their server. And we do it by just slamming in another flash rack, right? Which is far easier than upgrading the whole thing. It's far cheaper than if we just provided them with 40 in the beginning, because my cost of flash today is much more expensive than my cost of flash a year from now, and quite a bit more expensive than my cost of flash 2 years from now. For those of you who really think a lot about TCOs and amortization schedules, and I really don't think any of you do, like just looking at you, you don't look like the finance types, but if any of you are, being able to depreciate this over, say, 2.5 years, being able to depreciate this over like 5 years, this over like 7 years, it's far more cost effective than just having a single server that you just blindly throw out all the resources when, quite frankly, the DIMMs are still good, the flash is still good, the hardware is still good, but you're getting rid of the whole server because the CPU is a little slow. So in terms of strengths, disaggregated rack, it maintains our volume pricing, serviceability, things like that. We can do more custom configurations. It allows us to have hardware that can evolve with the service over time. We can do those smarter technology refreshes where we depreciate things a little bit more on the time scale that they essentially fail on. And I think that overall, this environment, combined with the group hug, is going to allow pulling away from those resources to being so tied to the CPU and give us a lot more flexibility with what CPUs we consume and how we consume them. That's about it for me, and I've got a few minutes if we have any questions. Yeah?
So the group hug, it's 10 arms. Are you guys envisioning a setup where you've got ARMs and x86, or is it all homogeneous in terms of the architecture, the computer architecture?
So for Facebook, we're only focused, one of our services is going to consume ARM, right? Changing instruction sets is a big pain in the ass, right? Nobody wants to do that. And putting up this oddball custom hardware, right, which is essentially anything new, if we're going to do it, we want to do it for a big win. And so for us, we're interested in ARM for the web tier. The reason that we chose the web tier, is Ali still here? Hey, Ali. So Ali runs the HPHP team, which is a fantastic project at Facebook where the original project was to take PHP code, translate it into C++, and then compile it for a web server, which resulted in a massive binary. It's kind of ridiculous. But it performed about 4 times more throughput. It was 4 times faster than PHP alone. That was years ago. Now the team has recently delivered a JIT, essentially a Zend replacement, where it's a bytecode interpreter that performs even faster than that original compiled binary. So now we've got a JIT, and we've got our bytecode that's platform independent, and now we take that and we just recompile our interpreter under ARM. Additionally, this entire team is they're big instruction geeks, and so they love this kind of stuff. So that's our first and only direction that we're going to go in with ARM. Of course, for us, it's a big win if it works out. Maybe wait a moment.
Do you employ virtualization in your infrastructure?
Absolutely not. So this entire approach is really the antithesis of virtualization. Virtualization, so hypervisors are really just nothing but overhead and inefficiency. I'm sorry, they are, right? If we have a service that is, so virtualization is fantastic when you've got 10 really idle servers and you can replace it with 2 moderately warm servers. And you can deal with the fact that when you go do a system call of almost any time, you're going to take 2 to 4 times as much time or resources, right? So if you can stick in user space, virtualization is okay. Anything that actually involves doing some work is sometimes problematic. Additionally, we, at least at Facebook, really push our engineers to efficiently use the hardware they're given. And if they're not using it, we go beat on them for some mutex that they've screwed up, or we just take servers away. So it's a very actively managed service. I think that's about it.
Yeah, nothing's about it. But,
Great.
Jason's around. Please ask me questions. The scale of what you do is kind of daunting.
It's fine.
Just from just sheer numbers. And I know there are some virtualization sessions later. Don't be downhearted, guys. There are other people that like you too.
Just not here.
Have a good rest of the day and enjoy it. Cheers.